Hello, good afternoon. So this is a talk about acids and bases, not meant to be comprehensive, but just to get you thinking about acids and bases. So with chemistry, you do need to spend plenty of time thinking about it, and also I think you really need to think about what's going on at a really small level. So first, we're going to look at a simple case, and you know something about acids and bases already, but we just want to make sure everybody's on the same page. If during this I ask questions, right, I might pause for a second. You might want to pause it and make sure that you can answer the question yourself. So first of all, we have this. We have this. So if we're going to say something about the pH of some solution that we're considering, we need to know the concentration of H+. So let's take a fairly simple solution. Let's take something like 0.5 molar, and let's take 0.5 molar of some strong acid. If I say strong acid, you should probably have 6 acids that come to your mind pretty quickly, probably 3 quicker than some others, but 0.5 molar, so one we'll just do HCl. All right, it's a nice strong acid. So we're going to do 0.5 molar, and I'm going to simplify this. We want to actually imagine what's going on with this H plus and then the Cl minus. So we know it's a strong acid. We know all of the protons are going to dissociate from the chloride. So inside here, what are we going to have? I'm going to represent this so that it's kind of easier to see. So I'm just going to write H. Now, I'm starting to write this. You can see that I'm already running out of room, and I've got chloride written there, and I've got H plus there. But I don't need the chloride there. I don't need to see that. Chloride is going to be a spectator in whatever happens, because protons are not going to stick to it. How do we know protons aren't going to stick to it? A proton's not going to stay joined with the chloride? Well, we know that because this is a strong acid. And if this is a strong acid, then it must dissociate in water. It's not. So I'm going to stop writing the chlorides. I'm going to erase these. They're not important to our discussion. So we can get rid of that. All right, so we're going to pretend this is 1 liter of water. This is 1 liter of water. And so each of these H pluses are going to represent 0.1 moles of H plus. So just so we define this. All right. So we have that. So this is 1 liter, and it's going to be magic. Okay, 1 liter, and we're making this simple. It's 1 liter, and it's going to stay 1 liter. It's going to stay 1 liter no matter what we add into it. We're only really thinking about the acids and bases. So we're gonna just pretend it's 1 liter. That way, it kind of simplifies the concentration, because what we want is the concentration of H plus. That's what we're thinking about. So that's important. All right, we have this. We have all this H plus. Well, what is the pH of this? Right. It's in 1 liter. I said it's magic. Right, but it's in 1 liter. We've got 0.5 moles. So right now I've added 0 hydroxide, so I'm going to put that in. I'll get to this in a second. So what is the pH right now? Well, the concentration is 0.5. So negative log of 0.5, and can we see that? Negative log of 0.5 is 0.3, yes. Okay. I got 0.3. Make sure you can see that. Yeah. We'll get to the graph in a second. So that's 0.3. Now what I'm going to do is I'm going to start adding a strong base. If somebody says to you strong base and nothing comes to mind, that's wrong. You need to think of some things when you hear strong base. We're going to add a very simple strong base, or a very common one, the one we usually deal with, I think, which is sodium hydroxide. So we're going to add in sodium hydroxide. Once again, I don't need to see the Na. I don't need to see Na plus here because that is going to be a spectator. So OH is going to come into the solution, and that's the only thing I'm going to consider. I'm only going to worry about that. And for each OH unit, I'm going to consider that to be 0.1 moles. Right? So same as the H plus was 0.1 moles, right? Each OH equals 0.1 moles. All right. So in comes an OH. Hydroxide. All right, they neutralize each other. We get H plus OH, we get water. All right, so now we look at it. What do we have left? Well, we have 0.4 molar, right? We have 0.4 moles. We said that it's still going to be 1 liter. We're ignoring, you're probably going to increase volume. We're ignoring that. So we see the H plus that is left. This is what we are looking at when we look at pH. We're seeing how much of this stuff is there. Some of it is gone, right? So we've added 0.1 moles, and now it is negative log of 0.4, which is 0.4. All right, do it again. Put in another OH. All right, now we have 3. So we've added 0.2. You can check this. You can make sure that you're getting these numbers with the negative log of that concentration of H plus. Let's add another OH. We got 2, so we've added 0.3 and negative log 7. Add another one. Keep going. We got 1 left. So let's see, we got 0.4. Oh, done. pH of 1. So our pH has gone from 0.3 up to 1. And we've neutralized a lot of the H plus. So let's add the last one. Do that. We've added 0.5. Now, notice we don't have any of the HCl left, right? We've actually neutralized it all. So what we have now is a solution of just water. So you should know the pH of water at 25 degrees Celsius. You should we don't even need to do that. We know that. I'll just put that in, right? It's pH 7. Notice the big jump there. That's important. Let's add another one. Let's just add one more, just to see something. We got OH minus. OH minus. We've got this. This is 0.1 moles of OH. So let's see. 0.6. So now we wouldn't take the pH, we'd take the POH. We take the negative log of the OH concentration. The OH concentration is 0.1 molar. Again, I said this was going to stay 1 liter. It's 0.1 molar hydroxide. Negative log of 0.1 is 1. The POH, therefore, is 1. So POH equals 1. pH equals 13. That's big. So you need to kind of get a feel for this. I think looking at it and seeing it just does help you a little bit. So let's plot this a little bit. Plot this on this graph over here. We got 0.3. Something like that. You see how steep that is. and this is going to continue on. Right? All right, so that's a simple case. We've got a strong acid. We're adding a strong base to it, and this is the curve that you're going to end up with if you look at pH versus how much hydroxide is added. Now, let's make it a little bit more interesting. Right? We'll think about what other things we can put in there. So let's still deal with 0.5. All right, let's still start with that. All right, I still have each one representing 0.1 moles of H+. Now, to this, we are going to add a weak acid and its conjugate base. All right, so there should be some weak acids which come to your mind. Many acids you can name would be weak acids. You do want to have some weak acids that you know the chemical formula, right? You can think of it. So maybe hydrofluoric acid came to mind. We're not going to deal with that. Too dangerous even to put on the board here. We're going to deal with acetic acid. So if you like vinegar, this is nothing like vinegar, but there's vinegar. CH3COOH, right? We could just put that right in there. That would be fine. But what we're actually going to do is take the weak acid, and what we're going to do is take that vinegar, and we're going to pour some of its conjugate base into it. The conjugate base would just be acetic acid without this proton. So it would be the acetate ion. Probably sodium acetate is what we would use. I'm not going to show the sodium. Again, the sodium is a spectator, but I am going to show the acetate. All right, so I put 3 units of each. Right? We're going to use the same, it's going to represent the same amount. So this is 0.1 moles of acetic acid. This is the same thing. So we've got 0.3 moles of acetic acid. Here we have 0.3 moles of acetate. So if we look at this, we think, okay, well, how do we classify that? What name do we give this type of mixture? Right? It's not important what volume this is in right now. And you'll see later, it really doesn't matter what volume it's in. But we have a specific name for this. But right there, what we have, weak acid, conjugate base. So that acetic acid, that proton, that is going to, most of them are going to stay on the acetate. Most of the protons stay on the acetate. So when we write it just like this. Maybe I should go prove that to you now. No, let's just finish this. Maybe I should show it to you. All right, well, let's continue to get some comparisons. So I'm going to take this and I'm going to pour it into the hydrochloric acid. All right, and we'll see what we have when we do so. We'll pour this in. Again, this is going to be 1 liter, right? And that's going to stay the same no matter what we add to it. We're saying it's still 1 liter. It just simplifies the concentrations that we're dealing with. So if I put the acetic acid in. There we go. No problem. No problem. They have their protons on there. These protons aren't going to, it's not going to further protonate the acetic acid. So this is what we have. However, if we start putting this in, the acetate ion is going to accept these protons. Again, this is 0.1 moles. This is 0.1 moles. So if I put, right, they come together. together. Right? So it might be a little bit hard to see that, but you can see that already what we've done is we've taken 3 of them have been attached to acetate ions, and we're left with only 2. So the amount of free H+...
Ms. Young, can you please call extension 3200? Ms. Young, please call extension 3200. Thank you.
So, if you just look at this, just by dumping that in here, just by putting the acetic acid and the acetate, mostly it's the acetate that's doing something for us, we have actually gotten rid of the acetate, sort of, right? I mean, if you look, there's not what we would call acetate there. There's a small concentration, but most of them have protons on them again. So we need to think about what's actually in this container right now. It's not like before. Before we had acetic acid and acetate. Now we've got hydrochloric acid and acetic acid. So right now it is a mixture of a strong acid and a weak acid. That's what's special about that. I don't know. So what we've got here, we've got 2H plus that are free. So let's look. We've got zero added OH. We are going to do the same thing as before. We're going to add hydroxide to this, and we're going to see how the pH changes. All right, so if we look at this, we've got 2 of these free. That means it is 0.2 molar. So already we have a different starting pH because the acetate accepted some protons. So the pH is 0.2. Alright, now let's put a hydroxide in there, and I'll use a different color, maybe that's a little easier. And hydroxide, alright, that's the proton that hydroxide is going to accept first, right? That's the one that's... There's other protons here, but that's the one that's going to get. All right, let's do it again. All right, now what do we have? Now we have the hydrochloric acid has been neutralized, we could say. So now what we look at is we have 0.6 molar, right? It's 1 liter. You said it's magic, it's staying 1 liter. We've got 0.6 moles of acetic acid. Right now we have a solution of acetic acid. That's it. There's some other things, some spectator ions in there, but we've got acetic acid. Not this, right? Just acetic acid. So let's first get this pH. So what we need actually, we're not thinking about the hydrochloric acid anymore. What we need to know about is the acetic acid. All right, so I'm going to stop it right now. That way I can, I'm not sure how much memory can be uploaded to the website, but I'm going to stop it here. So I want to point out, like, it's a little bit different from here on in because we're not looking at the case of a strong acid. Now we're looking at a weak acid, and so some other things come into play.